Okay, so we want to talk about momentum now and do a couple examples from the lab. And so let's start with the definition of momentum. And momentum, P, is just the product of an object's mass times its velocity. Okay, so mass times velocity, P equals mv. And we were hoping to get to momentum this week in lecture, but of course I was sick. But in any case, hopefully, even if you were a little confused throughout this procedure, this video should help. Okay. Now, we have a condition called the conservation of momentum, or the law of conservation of momentum, that says if no external forces are present in a system. Okay, so if there are no external forces acting on a system, so nothing outside the system is coming in and acting, then we have this condition of conservation of momentum which says the initial momentum in a system must be equal to the final momentum of a system. Right, so however much momentum there is initially must equal the amount that is there finally. And what does this initial and final mean? Well, often it's in relation to something like a collision. However much momentum is in a system before a collision must be in the system after said collision. Okay, and in equation form, it looks like this, right? So the initial momentum of an object, or of the first object rather, plus the initial momentum of the second object must equal the sum of the final momenta of the two objects. And momenta are additive. Okay, so it's not really esoteric in any way. It really is. You take the first object's momentum plus the second object's momentum plus the third object's momentum, etc., 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 and that gives you the total initial momentum in your system. And then you do the same thing with the final momentum. You find each individual object's momentum, and then you add it up after the collision, and that gives you your final momentum. Okay, and so we can simplify this just a little bit in our case because we know that in the simulation, the second object, or the yellow stone, is always going to be at rest. And so if I have my second object always initially at rest, then it doesn't have any momentum because its v is 0. So I can really use this equation to perform the lab. Okay, this is the equation that we're going to use to form the lab. Don't worry about the kinetic energy, okay? Don't worry about the kinetic energy equation. This is more or less there as a tool to distinguish between the two types of collisions, but in our case we're only going to consider one type of collision, so this is not really a necessary component to look at here. Okay, so let's actually dig into the procedure. And the first part of the procedure, we want to look at when the masses are the same. And what we want to do is set both masses to 10 kilograms and the initial speed of the redstone to 2 meters per second. And that's what we have here. And so if I just click on the redstone, let's see what happens. And sure enough, right? And what I'm given here are the final velocities of the two objects. And you'll notice that the redstone is 0 and the yellow stone is 2. Now, is this equation verified? Okay, is this equation verified? So we know that the mass of the redstone was 10 kilograms and its initial velocity was 2 meters per second. And the product of m times v would then give me 20 kilograms times meters per second. The final velocity of the redstone is 0, so that term drops out. And the final velocity of the yellow stone was also 2, and its mass was also 10. So that gives me a final momentum of 20 kilograms times meters per second. And so in the first trial, the law of conservation of momentum is verified. But what if I change the speed? Okay, so what if I change the speed, and let's bump this up to, let's do 4, right? And the computer's going to freeze for a moment. And let's see what happens here. And sure enough, 4 meters per second. Okay, so in the first trials, you should find that everything is verified perfectly. Okay, now in a real world situation, this would be very, very close, but the final velocities would not really be completely perfect, especially depending on what measuring devices you used to measure their initial and final velocities with. Some devices are much better than others, right? But in any case, in the simulation, it is verified. But what about the other situations, right? So let's come back over to the PowerPoint. And what about when the masses are different? So now we're going to leave the red stone at 10, but the red stone is going to be less massive than the yellow stone. And so we're going to set the yellow stone to 12. Actually, I'll tell you what. Let's come back down here into this table, and just to give you an example, the best example, let's set the yellow stone to 16. So let's make the yellow mass 16, and we'll reduce the red stone's velocity back to 2. Okay. Now, what should your prediction be? Well, if an incoming object collides with a stationary object that's larger, you might tend to think that the stationary object is going to move in the direction of the initial object, and the initial object will then bounce back. And let's see if that intuition is correct. Sure enough, right? We see the red stone bouncing backward and the yellow stone moving forward. Right? So let's keep an eye on this information right here. The velocity of the red stone was 0.46 meters per second, and this at 180 degrees means that it went backwards. All right. Now remember, momentum is a vector, so direction, magnitude, and direction are important. So if we consider the red direction moving to the right initially as a positive velocity, then the red stone moving backward would be a negative velocity, okay? And the yellow stone being knocked to the right would also be a positive velocity. So we're going to keep that information in mind, and what I've done is I've constructed a table here in Excel that matches the table here, except that I've also included the mass of the red stone, which will make it easy to calculate the initial momentum of the system, right? So since the red stone was the only stone that was moving, then the initial momentum is going to be all wrapped up in the motion of the red stone. So what I'm going to do to calculate the initial momentum of the system, I'm going to type in an equal sign, and then I'm going to punch in the mass of the red stone times 2, and that's going to give me the initial momentum. And then I can just click and drag, and the formula will hold. So the mass of the red stone times 2, mass of the red stone times 2, etc., etc. But we're looking at this bottom one down here. And the category for the red stone final velocity, I'm going to come back into the simulation. The red stone had a final velocity of 0.46, but this at 180 degrees means that it was in the opposite direction of its initial motion, which means that I have to give it a negative sign. So I'm going to give this a negative 0.46. The final velocity of the oops, hang on. Let me do this. There we go. I didn't actually fill in a cell that I thought I had. So we're going to look at the Yellowstone final velocity, and it was 1.54. And now what I'm going to do to calculate the final momentum, I'm just going to take the mass of the red stone times its velocity plus the mass of the yellow stone times its velocity and calculate the final momentum. It should be close to 20. And let's see what happens here. So I'm going to take equals mass of the red stone times its velocity, the mass of the red stone times its final velocity, plus the mass of the yellow stone times its velocity. And I get 20.04, which is indeed close to 20. And then to calculate the percent error, I'm going to take 20.04 minus 20 divided by 20. Since 20 really is a theoretical value, but it really is also a perfect value. So there's no rounding in that value, for example. Okay, and then multiply that by 100, and I get 0.2. So the difference in percent between my final momentum and my initial momentum is 0.2%. Okay, that's a very small percent error. And in fact, the reason there's any error whatsoever here, because this is a simulation, is in the fact that this only takes out to 2 decimal places. Okay, so if it took out a couple of more decimal places, this would be darn near exact. All right. So that's how you do the second part. Okay, that's how you do the second part. What about the third part? Okay, so let's come down here to the third part. And actually, let's look at here first. So now we want to set the redstone to 25 kilograms, and we're going to set the Yellowstone to 10. So in the previous case, we had the redstone being less massive than the Yellowstone, but now the redstone is going to be more massive than the Yellowstone. So let's come back into the simulation, reset the system, and we're going to increase the mass of the redstone up to 25. Okay, and we'll take the Yellowstone back down to 10. And so that will be this first trial here. Okay. Now again, we know that the momentum of the system initially is going to be the mass of the redstone times 2, which is going to be 50. And we now want to run the simulation again, and this will give me the redstone's final velocity and the Yellowstone final velocity. So let's come back here and let's go. And this time they both move in the positive direction, right? And so here the final velocity of the redstone is 0.86. So let's put that here, 0.86. And the final velocity of the Yellowstone is 2.86. Oops, let's do that. And so the final momentum here is going to be equal to mass of the redstone times its velocity plus the mass of the Yellowstone times its velocity, and I get 50.1. And so then the percent error is going to be 50.1 minus 50 divided by 50 multiplied by 100. And there we go. So again, 0.2%. So these percent errors are incredibly small. Okay, 0.2%, which is very, very small. But hopefully that gives you an idea, okay, of how to do the lab and what we're looking for. And that should also help drive home the idea that momentum is indeed conserved. Okay, and so I hope that you found this video helpful. And if you have any more questions, do not hesitate to contact me. All right, we'll see you next Wednesday.